Hello everyone. I think this is the last lecture. Yeah. The previous lecture covered the concepts of big data and why we needed big data. I explained to you with examples that all the modern applications like social media are cloud-based, and they work with complex data sets. Most of these complex data cannot be accommodated with traditional RDBMS because modern applications um, rely on databases which are largely schema-less, um, and the only way to manage such complex data is to take a different approach to storing data. Um, so the complex data set are so huge that we call them as big data. Towards the end of the last lecture, we also discussed the CAP theorem, the CAP theorem, and we gave you some examples on how different database systems implement the CAP theorem. In this week's lecture, we look at big data storage and processing, and the tools you will study would be NoSQL and Hadoop. I know I made reference to Hadoop in last week's lecture when I was discussing big data. Some of the concepts I explained last week have to be related to our discussion on Hadoop. Hadoop is one of the most common big data management systems. We will look at the implementation principles of Hadoop and how the distributed data management system works. And we'll also be discussing some of the common operations performed with big data, of course, which will be clearer when you start doing the lab tasks. So the lecture agenda for this week is we are going to be comparing acid and base, that's ACID and BASC. You will see as that acid implementation is standard, which is used across the traditional RDBMS. The base standard is used with NoSQL systems. So we look at the difference between the two implementations. Then we look at what a NoSQL database is and what operations can be performed on it. We specifically look at MapReduce, which are actually two common operations with big data, which is map and reduce, but we'll come to that later on. And finally, there will be a discussion on distributed data management with Hadoop. So let's kick off this discussion with the acid and base standards. Well, database professionals know the terms atomicity, consistency, isolation, and durability. That's what comprised within acid. So atomicity, consistency, isolation, and durability. So this is a part of the acid system. This has existed for many decades and has been associated with the traditional databases. It's a primary benchmark or a metric. You know, it would be ideal to achieve all of them, but it's not going to be possible. Um, so the ACID standard is vital to ensure the reliability of the overall system. So the traditional relational database systems try to achieve as much as possible within the ACID standard. On the other hand, we have the base standard, which is used by modern distributed database systems and big data systems, for example, NoSQL systems. So I might have explained this before, but we will still quickly look at the meaning of each term in ACID. Atomicity means that the tasks are taken towards completion, right? So the tasks are taken towards completion. In other words, all tasks within the transaction should be completed, or none of them should be completed. So that's it. If it's going through a transaction, it should be completed, or none of them should be completed. Therefore, if one task within a transaction fails, then the entire transaction must fail, and this is what atomicity means. Yeah. Consistency means that the system must always follow the protocols for the transactions. And the protocols, the rules of how the transactions must be completed is defined by the system, right? So consistency means following these rules. Again, this is to ensure consistency at the beginning of a transaction and at the end of the transaction. If the system follows the protocol, there won't be any incomplete transactions. All right, so the transaction have to be consistent. It cannot be incomplete. The next one is isolation, where no transaction has access to other transactions, right? So no transaction must have access to other transactions that are either incomplete or unfinished. Each transaction should be independent in what they do. All right. So once again, this assures consistency of transactions and always ensure that there is a reliable state within the system. The final one in ACID is durability, which means that once the transaction completes, that action cannot be revoked by a system failure or other types of issues with the system. So the system must be durable. All right. So the four properties I've just explained within the ACID forms the RDBMS or relational database gold standard. So traditional databases are measured against how well they are implementing the ACID standard. But of course, we are in the area of big data and schema-less databases. So it won't be possible to apply ACID schemes, ACID standard to modern databases, right? So ACID is mainly related to RDBMS. But if you're looking at the current situation with big data, it won't be possible to apply the ACID standard because current databases, the cloud-based databases, are largely distributed in nature. All right. So because current databases don't have schemas, it would be impossible to measure their efficiency with ACID. So we need a different standard, and that is the base standard. It's called the base, which is what you see on your screen at the moment. So base properties, let's compare base as opposed to ACID. So B stands for basically available. Recall from last week's lecture that modern databases need to implement the CAP theorem. Does that ring a bell? The CAP theorem? Basically available means the system is able to guarantee availability of the data. That's what it is, right? Data being available at all times. As long as the CAP theorem is implemented accordingly, data must be available to the users, to all the systems, all right? If a piece of data is not obtainable due to being inconsistent, for example, or when data is going through a transaction, the system will respond that it is unable to access the data because the data is inconsistent. All right. So whatever consistent data is there, it should be always available. Whatever data is going through a transaction or which is inconsistent should not be available, which is fine. But in which case, you will get a message from the system saying that that's what's happening. The next one is soft state, which acknowledges soft state, the phrase soft state acknowledges that a system could change over time, which is what would happen on a big data system or a distributed database. So the system would change over time even without input, right? There's this ongoing this set of transactions, right? So this evolution, right? And that sometimes could happen even without any input, right? So there's always some data that's going through some transaction. This is what we mean by soft, right? Soft is, it's not hard, obviously. It's not concrete. It's fluid. So it recognizes the fact that things in the database are going through achieving eventual consistency. All right. So the soft state means system is not consistent, but it's working through towards eventual consistency. So anything intermediate is considered as soft state. Anything intermediate is considered as soft state. The final stage would be eventual consistency. This means that the system would eventually become consistent. Right? When there is no input, when nothing happens, eventually the system achieves a consistent stage. Of course, we're talking about a distributed database, so this consistent data must be replicated. So think about this, right? And I know it's starting to get complicated now. So think about this. So with distributed databases, the data is spread across different, servers or data centers or whatever. So when one copy is supposed to be consistent, that has to be replicated across multiple sites, multiple data centers. All right. So that's what system becoming eventually consistent means. So the entire system, every single copy of the data is consistent overall. All right. So while it tries to achieve overall consistency, the system might still continue to receive input, right, resulting in the data being changed. So if that's the case, it might decide to defer the updates. All right. So yeah, so the key phrase we are focusing on is eventual consistency, right? Eventual consistency. In other words, consistency will be achieved at some point, all right? So you guys might have heard of NoSQL. I think most of you have heard of NoSQL, which exactly means that it's not structured. It's not structured query language, right? There are slight elements, but it's not SQL based. So again, go back to thinking about the system where data is so unpredictable. Data is so unpredictable, and data types are unpredictable. So what about situations where we are dealing with unstructured data? What about situations where we are dealing with humongous data? The point I'm trying to make is we need some form of storing data that is unstructured. All right. Traditional RDBMS work on structures and schemas. That's how it is. If you go to databases, the traditional database, not big data, traditional databases, they would always need some structure, and they are always based on a schema. But that is no longer the case with the kind of data sets we are dealing with in modern days, with modern applications. Hence, we have the NoSQL databases, and some of the examples are given there on the screen. Things like MongoDB and Cassandra. So what we require for our current data storage and data processing needs is, remember this, is a more agile approach to storing data. We need a more agile approach to storing data. I have mentioned the word schema-less many times before, so schema-less. And what that essentially means is that the data is unstructured. Not just the way we process data, but it's a lot more complex than traditional database approaches. So the data we store currently is quite dynamic, and hence not suited to be used with RDBMS. The problem with using RDBMS is that when data is unpredictable, an RDBMS system would find it very difficult to accommodate that. All right. So the bottom line is you should only use RDBMS. You should only use RDBMS, the traditional RDBMS, if you know, only if you know that your data set is simple enough to follow a rigid schema. All right. If you know the structure, if you know the schema very well, go for RDBMS. But if your data set is not simple enough to follow the rigid schema, you will need something like NoSQL. The slide shows some of the common features of NoSQL. Of course, it is non-relational, like we have established before, right? And it does not follow any particular schema. It is a very cloud-friendly approach and something which fits in with the distributed model of data management. It is horizontally scalable. We discussed about scalability in last week's lecture. What that means is that we're able to easily grow, I suppose, the distributed system. Okay, we just are able to grow or develop the database by distributing it across multiple servers. Although it is very complex due to the distributed nature, it is still possible to achieve very fast data access. All right, very fast data access. Yeah. And of course, many of the NoSQL databases you work with are open source and have a large community of developers who contribute. NoSQL is a radical way of thinking about databases, which and it doesn't follow many of the database principles. You know, the things we learned about RDBMS, all the principles, most of them won't apply for NoSQL. All right. As the name indicates, NoSQL does not use structured query language to process or manipulate data. No, it doesn't do that. So it might sound really weird talking about all these databases that don't use SQL. Does it sound weird to you? Okay, because someone talks about database, normally you associate SQL. How do you query a database? Oh yeah, you use structured query language, right? But that's not how big data works. All right, you still query the database, but there are different ways of doing that, but it's not through SQL. All right. So yeah, NoSQL database are different in the form in the way that it handles data. So it can take many forms. It can take many forms. For example, key value store, document store, big table, graphs, etc., etc. All right. MongoDB, for example, the one which I mentioned the last slide, MongoDB follows the document model. Each row is considered as a key document pair. So a document is associated with a key, right? So the key is used to identify the document. I'll explain this later on. So it can hold a collection of documents. So that's just one example, right? So many of them. So yeah, more characteristics. Like I said before, NoSQL databases can take multiple data structures. For example, I mentioned the key value pair, graph, document. So this will obviously take different forms. Because the reason we have so many types of NoSQL database is because data complexity takes different forms. All right, a NoSQL database must be able to accommodate the complex data structures. All right. NoSQL databases are not expected to follow ACID because, as you know, ACID is applicable to traditional databases. So there is some degree of flexibility when it comes to applying those principles to NoSQL database. Also, with regard to the CAP theorem, NoSQL database can decide to implement AP or CP. Okay, so NoSQL database can decide to implement either AP or CP. Again, if you don't know what this means, please listen to the lecture from last week. I did explain to you what each element of the CAP theorem means. All right, so please go back to the lecture from last week. Yeah, because NoSQL databases are distributed and implemented on the cloud, that is replication support. I have mentioned about replication before. So data must be replicated because it's a distributed environment, obviously. So there is replication support. The final point there says easy API, which means that users are able to manipulate the data on simple APIs, which internally might be a slight variant of the SQL. But you will realize this when you work with big data, and you will appreciate that the operation supported by NoSQL is not anything. It's different than what you have done with traditional databases. As I've said before, NoSQL databases do not support relational features. I've gone on and about this. We just repeated the same thing because I want you to want you to understand the differences. So what this means is it doesn't support NoSQL doesn't support join operations, right? It doesn't support join operations except when it's needed for partitions. There is also no referential integrity. There is no referential integrity, um, which, well, if you have experience in RDBMS, you will know that referential integrity relates to foreign keys. So we don't have that in NoSQL. So yeah, the approach is, like I said before, it's quite radically different. So there are on the slide there are some examples of the categories of NoSQL databases. There are databases which organize data sets as a key value pair, which creates a mapping between a key and the value. These are highly partitional and can allow for horizontal scaling, probably more than any other type of database. Some of the applications which would benefit from key value organization are IoT applications, in the Internet of Things, where sometimes single digit millisecond accuracy, right? Single digit millisecond accuracy is required for applications. Although we cannot generalize the use of key value databases to specific applications, it is normally used in those cases where there is high write workload, okay, where a database is written into quite at a very high speeds, and we need low latency of data access. So yeah, so key value structures use dictionary or hash tables where a key serves as a unique identifier, if you like. Yeah, so we don't say primary key or anything. We just say key, a unique identifier to retrieve an object. Now this object can be as simple or complicated as you want. It can be either text or numbers, or it could be anything complicated. It could even be very complicated code or JSON structures. Then we have the column-oriented organization, where a key could represent the mappings between a set of columns and values. So look at the diagram there. So you've got a set of columns and values, and a key could represent all of this. So the key could represent the group. So the column-oriented databases are also known as columnar databases, and they store data in columns, as the name indicates, right? So now it might sound very similar to traditional databases. It might sound, because if you look at traditional databases, there's a concept of rows and columns and all that, right? So you might think, oh, how is this different? But it is actually different because the way NoSQL organizes the data is as column-oriented data, right? It's column-oriented data, which means that each column could be stored as a separate file or in a different part of a storage system. So again, just look at the diagram on the slide. What you need to understand is that in a column-oriented database, the data is stored in record order. The data is stored in record order. This means that the first entry in one column is linked to the first entry in other columns. I hope you understand that. So first entry in one column is linked to the first entry in other columns. So in the diagram there, look at the diagram again, value 1, value 2, value 3, etc. are all related. So when you want to run a query, when you want to fetch something from the database, you can only select those columns you need rather than reading every single row. Okay, you can actually select a subset of the data rather than reading everything. Does it make sense? The next one is document oriented, which indicates it stores documents, as you know. So it's document oriented, and the documents are identified by keys. Now, for application developers, this is a huge thing, right? It's because data can be stored as code or JSON document. You know what JSON is? Do you remember me mentioning about JSON a couple of weeks ago? JSON is JSON. Do you remember that? So document-oriented database is quite a useful approach to store and query data that fits their applications. The document store can be processed by users using the API, um, and the reason we have this is the document databases can support very complex structures, and you can also nest documents within within other document. It's possible to do that. Okay, you can nest one document, you can embed one document in another document and store it. So I've already given you an example of what kind of document can be stored. I mentioned JSON, but it can also store things like BSON or XML, etc. You can also store PDF documents and perform a full text search for data retrieval. So it can get as complex as you want, right? So these are quite popular because they have a very flexible schema, and it's typically used in those applications, those kind of applications which have e-commerce or data analytics or content management platforms, right? So they are very scalable. They are very scalable. So we have used the word sharding before to scale the database horizontally. So we have the graph database. Again, look at the diagram. So we all know what a graph is. Well, technically, a graph database is technically a subcategory of the document-oriented model. The only difference is that the graph database is able to organize the complexity within the document and its relationships, right? So what it does is that a graph database will create nodes to establish the relationships between documents or relationship within a document. If you have worked with graphs before, chaps, you will know what a graph looks like. It has got nodes, it's got edges, and it's got directed and undirected connections between them. So sometimes it is preferred to store documents as graphs because they automatically create the links between groups of information. So think about it. I mean, if there's a huge document, there is a lot of information within the document which are linked together. The best way to represent this would be as a graph. All right, rather than storing it as a plain document, you would prefer to store it as a graph. So that way you're able to establish the links between different groups of information within a document. Let me give you an example. Let me give you a very good example of where a graph database could be handy. Think about a scenario where we need to establish the relationship between individuals and their connections to other individuals. All right? So think about it. We need to establish the relationships between individuals and their connections to other individuals. What comes to mind? Can you guess? Did you think about social media networks? So social media networks, what's happening in social media networks? So you've got individuals, you've got other links with other individuals, right? So that's what it is. So that might be a very good example where graph theory can be used within a database to represent those complex connections to other individuals. Now other examples can be for applications that are used to detect fraud and to verify identity of the people. So what I want you to do is just think about other scenarios where a graph database could come in handy. Yeah, maybe it's worth making some notes on that. And then finally we have the XML databases, which as the name indicates is we store XML files. So here are some of the basic NoSQL APIs you would use. For now I'll explain it theoretically, but it will only make full sense when you actually try it out. But these are quite easy to understand. We have operations like get, put, delete, and execute. Um, yeah, the get will extract a value by the key. The put will create or update the value given the key. The delete will remove the key and its corresponding value. For the execute API, you would provide a key, the operation, and the parameters, and it will invoke the operation on the data structure. But also, one of the things which you often work with is MapReduce, which you will see soon in the coming slides. So what you can gather from all this is that these APIs are not based on RDBMS. They do not reflect on supporting relationships. All right, it's not about relational database at all. So they are not effective in supporting that. All right, so they're not even effective in supporting joins or aggregations. Does it make sense? Right. So what we are saying is we are again going back to the point I made earlier. We are taking a completely different approach to handling data. So there you have it. So here are some examples. Here are some examples of the storage schemes of various NoSQL databases. MongoDB belongs to the document-oriented category. Well, there are some overlaps, which means that some databases can handle multiple storage schemes, organization schemes. For example, Cassandra can handle key value stores and big tables. So yeah, so there's so many of them. Yeah. This diagram looks familiar to you, doesn't it? Yeah. So we have looked at the CAP theorem last week. So we have three elements within the CAP theorem. C, which is for consistency, which means all clients have the same view of the data. Mind you, this is a distributed environment, so consistency between data sets is often considered as a very important attribute. P is for partitioning, which means that the system should work well despite the number of physical partitions over the network. Right? So data set could partition across the network. Yeah, data set could partition across the network. And when the data set grows, when you keep adding data, the data set grows. And what we are saying is the system should still work efficiently irrespective of the number of partitions, okay, of the system or the data set. And yeah, A stands for access, which means that each client should always be able to read and write. The diagram shows which two of the attributes of the CAP theorem various databases implement. Can you make a list of the CAP implementation of various NoSQL databases? There are some examples given there, but if you can, just have a quick, make a brief list on which two of the CAP theorem the various NoSQL databases implement. Now we look at some of the most important operations on big data. You might already have heard of these before, and they're commonly associated with the big databases. There is the MapReduce. It's called the MapReduce operation algorithm, which is essentially two operations. Yeah, it's essentially two operations. It's rather two parts. The first part being mapping. First part is mapping, and the second is reducing. So first you have to map and then reduce. Let's see what these are in the coming slides. Right, chap. So because we are working with huge data sets, in parallel and distributed environment. We are working with huge data sets in parallel and distributed environments. We need a special framework to extract the data from the data set and to feed this data into further operations. So this framework is the MapReduce. It's a MapReduce. MapReduce is two parts. First one is map, which is an operation which takes a block of data. It takes a block of data and produces key value pairs as intermediate outputs. It creates a key value pair, right? So you put that within brackets. If you look at that, we have it says output of the mapper is a key value pair, all right? So that becomes an intermediate output. Now, once again, chaps, please think of this operation happening on a large-scale distributed network. All right. For example, the Hadoop file system, Hadoop distributed file system, or HDFS. So the map function works on a single block on the file system, right? But the map function will also be running on multiple slave nodes. So think again, go back to distributed environment. There are multiple slave nodes. There's data scattered all across the system, right? So the map function is going to work on the file system, which is held locally, or a slave node, all right, where data is stored locally. Each of these file system blocks provides the input to the map function, which then produces the key value pair. All right. I know it can get very confusing here, chaps, but hopefully the example in the next slide will make it clear. But yeah, just be with me for now, right? So just try to follow what I'm saying. So in simple terms, we have data chunks on the file system, right? This is provided to a mapper, which creates the mappings. In other words, it breaks down the input and provides the key value pair. Look at again the slide. That's within the brackets. We have said key value pair. So it creates a key and a value, right? It produces a key value pair. It extracts the key value pair. And this is the intermediate data tuple. So it's tuple, tuple, right? Then the reducer is used to aggregate. The reducer is used to aggregate the intermediate data tuples to create smaller set of tuples. All right. The reducer is used to aggregate the intermediate data tuple, which creates smaller set of tuples, which then becomes the final output. All right. Again, this may or may not be clear to you guys, but there are some examples in the following screens. There's actually a diagram which explains all of this. All right, so just try to be with me here for now. Right? But if you actually look at the process in detail, it consists of 5 stages. The first is input, and then splitting the input, which is then mapped, which is then shuffled, and which is then finally reduced. So it's actually a 5-stage process, but we say MapReduce, which kind of encompasses all the operations. All right. So the way to understand this better is, once again, guys, think of this process being performed on a distributed parallel environment. You will not be able to understand any of this if you think of this happening on a single system. No, it doesn't, because it's happening on a cloud. It's happening on big data. It's happening on the cloud. It's happening on a distributed environment. So you need to understand this. You need to try and contextualize this to the operations across different data centers, or different, or maybe even different nodes, right, on the network, right? So the map function works locally on a file system. For example, we have the Hadoop file system. Similarly, there are other local mapping functions elsewhere. So there are different map processes which happen locally on different systems, each depending on their own copy of the data. All right. So each mapping function provides an intermediate output, and this is sent to the reducer. All right, the reducer. And as I said before, the reducer's job is to aggregate all of this information. In other words, the reducer kind of summarizes all the input from the mapping function and it produces an overall output. All right. So yeah, this is a very simple example of the MapReduce framework, and it exclusively works on key value pairs. The input will be well, you see the input will be K1 V1 or key one value 1. Please note that this value can be complex. It can be as complex as it can be. So it could be even a large text file or more complex stuff. So what the map job does, it creates a key and a value pair. So again, there's a K. So we see K1 V1 becoming K2 V2. You know, so that's producing a key value pair, which is combined with the key value pair from across all the mapping functions in a distributed environment. Again, go back to what we said about data being distributed across various local systems or even on data centers. All right. So this result of the map function is fed into the reduce, which then aggregates all the key value pairs and produces the final output. And an example is given you on the slide, but you'll probably get a better understanding when you actually try this out on Hadoop. Try a simple example on Hadoop and try to make it more complex. All right. So just to give you a diagrammatic representation of the word count example. So this, let's go back here. So this example here is to count each word in a set of documents. All right. So count each word set of documents using the MapReduce. All right. That's this code snippet given to you. But if you expand that into a diagrammatic form, that's what you get. So in this representation of the word count example, it makes things easier to understand. So we have document 1, doc 1 is split, and we have line 1, line 2, and line 3. Please remember that this split could be happening across different file systems. Similar splits could be happening across multiple file systems on the distributed network. It is fed into the mapping function, right? So after the splitting stage is the mapping function, which creates the key value pairs for each of the lines. So you have deer 1, bear 1, river 1, car 1, river 1, etc., etc. So that's the mapping. So if you can see that, they're creating a key and a value. All right. Yeah, so it creates the groupings that way. Then it's shuffled, which means it's being put together. So we have all the bears coming together, all the cars coming together, all the deers coming together from various points, from various operations of the mapping. All right, and then finally we have the reducing stage where we get the aggregate of the overall result, and that's when we have the final result, which creates a set of values mapped to their keys. All right, or rather, in this case, we have the values and the count of how many times that word has appeared in the document. So I hope this is clear, and you might want to explore this further with implementation using a programming language. As a matter of fact, the MapReduce framework has implementation in different programming languages. So yeah, take your pick, and then you can implement in whichever programming language you want. So, like I said before, chaps, I think I'm having the risk of repeating myself here. All right. So all of this will only make sense if you think of the entire environment as one large distributed environment. That's what it is. So it's capable of parallel processing, and that's the essence of MapReduce function. All right. So the mapping creates localized key value pairs in the distributed file system and reduces and then it's reduced to create the overall summary, if you like, or the overall output. All right. So like I said before, you will have difficulty in understanding this if you only focus on a single point on the network. So look at the words we have used: the parallel processing, data locality, right? So yeah, so the MapReduce task takes place on large data sets on large distributed networks. Okay, the purpose of the MapReduce framework is to hide this complexity from the user. There is no way a user can do the map and reduce separately, and it's too complex. So they use the framework to make things simple for them. All right, it hides the complexity from the user. So yeah, what is Hadoop? It's Apache Hadoop? So I've already mentioned about the Hadoop distributed file system, the HDFS, that stores data on commodity machines, and one which supports batch processing. So we have already discussed batch processing in one of our previous lectures. Yeah, it's open source framework for storage and processing large data sets. All right, and again we're talking about distributed clusters here. And we already know about the MapReduce programming model, but it has so many other features which are very useful for big data processing. So these are the Hadoop principles. It's a scale out rather than scale up, a concept which we are all familiar with, and something that has been explained so many times before. All right. So Hadoop is to work on design. Sorry, Hadoop is designed to work on commodity, unreliable hardware, which is usually the kind of hardware we users normally use, right? The process um, is the Hadoop file system will works on the basis of bringing code to data rather than data to code. It is not possible to take data to code because the data is obviously distributed, as we all know. It would be easier to tell localized pieces of code to process the data locally, which then feeds into the overall output. All right, and this makes sense because with regard to the MapReduce you have just seen. All right, so it's easier to take code to data rather than data to code in a distributed environment, and that's what we do with the MapReduce as well. And Hadoop is designed to provide fault tolerance. It knows that failures are common, so it knows how to work in a distributed environment that is subject to failures, and it should still be able to work efficiently. All right. So the bottom line is Hadoop acknowledges the complexity of distributed concurrent applications. Well, I won't go too much into this, chaps. That's the Hadoop stack. That's how it looks, and I will let you make some notes on some of the key components you see there. It's actually a lot more detailed than what's shown on the slide. So we have the management layer, which contains the components to do the workflows and monitoring and management. Then there is the data access layer with the components for data flow, machine learning, etc., etc. And the data processing layer has the MapReduce framework, which we have just seen. And underneath all of this, we have the file system, the Hadoop file system, HDFS and HBase. So this diagram summarizes the operations that happen at a node level. Again, guys, you could accuse me of repeating myself here so many times. But yeah, please try to understand this in the context of a distributed environment. The mapping process, as you can see from the diagram itself, the mapping process takes place at each node level, right? So mapping process, within the MapReduce, the mapping process takes place at each node level under each file system level. Alright. So the output coming from each node is a key value pair, and what you have to understand is that there is likely to be duplications in the key value pair across the nodes. So as it is, the values coming from these individual nodes are of no use. Alright, so the values coming from these individual nodes are of no use unless they are aggregated. Alright, so this intermediate output from the mapping process is aggregated, and that's what the reduce process does. So reduce is reducing, or rather consolidating, the key value pairs coming from the various nodes, and this creates the final output for the various nodes to use locally. All right. There is nothing much to say about that slide really, except that all cloud providers offer database as a service, DBAAS. So all cloud providers offer database as a service, and some examples are given there, and they're all big database services. So yes, so the yeah. Yeah, I know that makes your head go dizzy, chaps. Yes, but that's the big data landscape. There are so many players, so many providers, and yeah, so much to learn. There is no way we can learn all of that. There's no way anyone can learn all of that. But the expectation is that once you learn the essential skills with big data, the skills are transferable. They should be transferable to other big data platforms. All right. So yeah, that's the last slide, chap. So I think this is the again, like I said, this might be the last ever lecture. So please keep up to date with your lab sheets, and you'll have your assessment soon. So all the best. Thank you.